So for all the speakers, I will give you, so we have a mix of talks. Some of the talks are 20 minutes in this session, and some of them are 18 minutes. We will reserve 2 to 3 minutes for questions and discussion. So I will give you warning for 2 minutes before your talk is supposed to be over. So for Luciano's talk, it's 20 minutes talk. So I will give you warning, the warning at by after 15 minutes passed, so that you can wrap up your talk in 2 minutes, and then reserve 3 minutes for questions. And for 18 minutes talk, I will do the same. I will give you the warning at 13 minutes past, and then we reserve 3 minutes for question as well. For questions, you can either type it in the chat or use the raise hand feature at the end of the talk. And we will go through the list in chronic order. So please keep the time of your talk so that we can keep the schedule as planned. All right, so I think we are ready to start the session. The first speaker is Luciano Pappalardo for the Hermes collaboration. So please go ahead.
Yes, do you see my slides in full screen?
Yes.
Okay, perfect. So good morning, everybody. I will present the latest Hermes results on azimuthal single and double spin asymmetries in semi-inclusive DIS using transversely polarized protons. So I don't have to explain you what TMDs are. Let me just highlight the main features. So first of all, TMDs constitute a more general family of parton distribution functions, which depends not only on the longitudinal momentum fraction carried by the parton, but also on its intrinsic transverse momentum K-perp. And as an example, you see here as the Sivers function for the hub quark as a function of the quark transverse momentum for 5 different values of the longitudinal momentum fraction encoded by the X-Garten variable. Now, TMDs are extremely interesting objects because they encode flavor-dependent correlations between the transverse momentum of the quark and the spin orientation of either the parent hadron or the quark itself. And this correlation makes them also sensitive to the unknown quark orbital angular momentum. And they also provide 3-dimensional descriptions of the nucleon structure in momentum space. You see here as an example the densities of the up quark in the transverse momentum plane. It is clearly asymmetric with respect to 0 due to the correlation that I was just mentioning. And one is able to provide pictures like this for different value of the longitudinal momentum fraction. This is exactly what we mean by the nucleon tomography. Now, at leading twist, as you know, there are 8 different and independent TMDs. And up to now, the golden process to measure these quantities is a semi-inclusive deep-inelastic scattering, where essentially 1 or 2 of the final state hadrons is detected in coincidence with the scattered lepton. And you see here the full expression of the SIDIS cross-section up to subleading twist term. There are plenty of terms here, each is described by a specific structure function with this capital F, and each depending on a specific combination of the azimuthal angle phi and phi s, which are defined here. So phi is the azimuthal angle between the scattering plane and the hadronic plane, where the final state hadron is produced. And phi s is the azimuthal angle of the scattering plane with the transverse polarization vector of the target. So in the last 15 years, the Hermes experiment has played a crucial role in these studies. It essentially was able to measure all these objects, or to measure quantities that are sensible to all these objects. But today I want to focus your attention to this part of the cross-section, which essentially requires a transversely polarized target, either alone or together with a beam helicity, because we recently published all the results for all these objects you see here. So the paper appeared in the archive in July and was published in December last year. So what do we have here inside? So this paper essentially is a compendium of all the Hermes TMDs results obtained with a transversely polarized target. It is a rather long paper, above 80 pages, so this is why we like to call it the Hermes TMDs Bible. It provides the results for 10 different azimuthal modulations, 6 single spin asymmetries, and 4 double spin asymmetries, also requiring a longitudinal polarized beam. The results are provided for 7 different hadron types and in 2 different prescriptions. The so-called cross-section asymmetries, which encode the entire Fourier amplitude of each cross-section term, and this is what we have been using to publish in the past, and a new prescription, which is the structure function asymmetries, which instead represent pure ratios of structure functions. So in a sense, these objects are corrected for the epsilon-dependent kinematic prefactor that enter the various cross-section terms. So what is new compared to the previous analysis and the previous publication? First of all, we provide for the first time result in a three-dimensional binding in the three relevant variables, x, z, and pH perp. Before was only one-dimensional. We provide for the first time results for the proton and anti-proton together with the pions and the kaons. And for this analysis, we use the later data production, which includes updated tracking and alignment information. The extraction of the neutral pions asymmetry has been improved in various aspects, including the background subtraction. The one-dimensional binding has been optimized and also extended to this high Z region, so from 0.7 up to 0.2, which is beyond the standard the SIDIS region. And we like to call this the semi-exclusive region because it's essentially a bridge between the pure SIDIS and the pure exclusive regimes. And finally, we also extend the X-Bjorken range up to 0.6 before it was up to 0.4. So all the relevant asymmetry amplitudes were extracted in an unbinding maximum relative fit of the Fourier decomposition of the cross-section in terms of the two azimuthal angles that was defined before. And this is done separately for the cross-section asymmetries and for the structure function asymmetries. And you see here the likelihood function that we maximize to get these asymmetries. Now, this table summarizes our results. So we have here the 10 different azimuthal asymmetries, some of which come with a specific name. We have here the 7 different hadron types. And wherever we find a tick in this table, this means that the result is significantly non-zero, or to be more precise, it is incompatible with the null hypothesis at the 95% confidence level. Whereas when the tick is in parentheses, this means that it is incompatible with the null hypothesis at the 90% confidence level. Otherwise, wherever we don't find anything, this means that the corresponding result is consistent with zero. So of course, I will not have time to cover all these results. I will only focus on those that provide the largest signal, but clearly you find all of them in the backup slide of this presentation and of course in the paper. So let me start with the Sivers amplitude for the pi plus. Okay, you see here as a function of x, z, and pH perp. These are one-dimensional meanings. And we observe large positive amplitude, which clearly provide an evidence of a non-zero Sivers function for the hub quark. And the signal is observed to rise with x, z, and pH perp in the semi-inclusive DAS region. Now, of course, we can learn more when we now look at the three-dimensional projection for this quantity. So it is still the Sivers amplitude for the pi plus as a function of the transverse momentum pH perp for 4 different bins in z and 4 different bins in x. And the three-dimensional projection essentially confirm and further detail the rise of the amplitude at large x, z, and pH perp. What about results for the pi minus? So the results are essentially consistent with zero, and this was already interpreted long ago as due to the cancellation of opposite Sivers effects for the up and down quarks. Now let me focus a little bit on this semi-exclusive region, so this large Z region. Where you see here, essentially, there is a sudden change in the slope, which reveals a sudden change in the mechanism as well. So this is now understood to be due to a relatively large contribution from pions, which are produced from decay of exclusively vector mesons. So we studied this in the simulation with Pythia, and here we report the fraction of pions stemming from decay of vector meson divided by the total. And we see that if you look at the black point, which are those for the pi plus, that this fraction rises with Z and becomes quite substantial in this large Z region. We do have also here the same conclusion, essentially, because in this high Z region, the asymmetry is not zero anymore, but it is quite large and negative. So, of course, part of the explanation can be the same as before, which is where this effect is even more enhanced for the pi minus than the pi plus. But there could be also a concurrent or alternative explanation for this, that at large Z, the favored fragmentation, the one that provides the pi minus from the fragmentation of the D quark, prevails over the disfavored one, the one coming from the U quark. And so, in fact, in this region, we don't expect a cancellation anymore. And in fact, we observe an asymmetry which is non-zero and opposite in sign with respect to the one with pi plus. Now we have results also for the pi zero. The results are slightly positive, and the magnitude, as you see, is essentially intermediate between the pi plus and the pi minus one. And this is also expected based on the isospin symmetry applied at the amplitude level. When we look here at the high Z for the pi zero, however, we don't see any change of sudden change of the mechanism or the slope here. And in fact, also this we can interpret as due to the fact that the contribution from vector measurement is pretty small for the case of pi zeros. Okay, so essentially we can claim here that the observed positive signal cannot be attributed solely to the contribution from vector measurement at least. Now we have results also for the kaons. So these are the k plus series amplitude, which are large and show a similar kinematic behavior as the one for the pi plus. And as usual, we can learn more when we look at the three-dimensional projection. So you see here how the amplitude evolves in the large Z and large X region as a function of pH perp, for instance. And these are the results for the K minus, which are actually non-zero. So the result is different than we observed for the pi minus. Here, the amplitude is actually positive, but there is in practice no reason to expect a similar behavior as for the pi minus because they are completely different objects. The K minus is a pure C object, and it has no valence quarks in common with the target proton. Now, it is interesting to compare the pi plus and the K plus amplitude. And as you can see here, although they exhibit a very similar kinematic dependence in the same inclusive DAS region, the amplitude for the K plus is significantly larger. Okay, although they are both expected to be mainly produced from the scattering of U quarks. Of course, they differ in the C quark content. And in addition, there could be a different K perp dependence of the fragmentation function for these different C quarks, which might impact our asymmetry through the convolution integral. But there could be also another effect here. That could be a different impact of higher twist effects, for instance. So this we studied back in our old publication, which is from 2009. Essentially, what we did here is that due to our strong correlation between X and Q square, we split each X bin into two Q square region, a small Q square region where the Q square is smaller than the average Q square of that bin, and a large Q square region where it is larger than the average. And we compared the two subsamples for the pi plus and the K plus. And while we don't see any difference for the pi plus case, we do see a small but systematic shift for the case of K plus, which hint at the suppression at larger Q square for the counts. And it's also interesting to look at the large Z here. For the K plus, we don't observe a change of the amplitude or a sudden drop here. Actually, the amplitude keeps rising. And this can be understood because we know that the contribution from exclusive vector measurement decay is much less pronounced for kaons than for pions. Now, as promised, we also have series amplitude for the proton and antiproton. Actually, the result that you see here are the first measurement of Sivers asymmetries for proton and antiproton in SIDIS, and they are both non-zero. They are both positive, as you can see. It is interesting to compare the proton asymmetry with the pi plus symmetry. You see that within the uncertainty, the two are consistent, but of course, the proton asymmetry suffers by a large systematic uncertainty. And there is an important point, however, that is the following. So the proton production is particularly susceptible to receive contribution also from the target fermentation. So from the fermentation of the remnant of the proton. And this is expected to be especially enhanced at low Z and high pH perp. And a way to see this is, for instance, to plot the ratio between the yields of proton and antiproton. And you see when you go in the low Z, you observe here a change in the slope, which might indicate the onset of the target fermentation regime in this area here. So we decided to study this into more detail. We know, of course, that there is no generally accepted recipe for distinguishing between the current fermentation region and the target fermentation region, but it is also generally accepted that a positive X-Feynman or a positive rapidity are associated with the forwardness of the process. And so, in other words, they are associated with the hadron being produced from the struct quark, so the current fermentation region. And oppositely, the negative values of these two variables point at a target fermentation. So you see here the X-Feynman versus Z for the K plus and the proton. For the case of the K plus, essentially all the data are in the positive X-Feynman hemisphere, whereas if you look at the proton, we do have some small contamination from the negative X-Feynman. So we studied this into more detail. You see here the distribution of X, Z, and pH perp for positive X-Feynman in the upper row and for negative X-Feynman in the lower row. And here we can learn two things. First of all, of course, that the large majority of the data come from the positive X-Feynman region. But when we look at the negative X-Feynman data, which are a very small minority, then you see that they concentrate indeed in the very small Z and in the very large pH perp regions. And a similar answer we get when we look at the rapidity variable. You see here a rapidity in two-dimensional binding in Z and pH perp, and it is everywhere positive for protons, except in this corner here, where we do have some negative contamination, which indeed arise from the small Z and large pH perp kinematic corner. So in general, we can say that at the selected kinematics, the vast majority of protons are compatible with being produced in the current fermentation region. Now, let me move on to the Collins amplitude. These are the results for the charged pions, which are both large and come with opposite sign, again revealing a clear evidence of a non-zero transversality function. And this large negative pi minus amplitude has been interpreted already long ago as due to a large disfavored Collins fragmentation function, which is opposite to the favored one. Again, we can learn more when we look at this in a three-dimensional binding. You see, for instance, how the amplitude evolves as a function of x Bjorken for different binds in Z in the large pH perp region, for instance. Now the results for the pi zero, the Collins amplitude for the pi zero, these are essentially consistent with one and with zero, sorry. And again, this is an intermediate result between pi plus and pi minus. And again, we can interpret this as due to the isospin symmetry applied at the amplitude level. These are now the Collins amplitude for kaons, so k plus and k minus. If you compare the two, you see that the k plus exhibit a very similar kinematic dependence as the pi plus, although the amplitude is twice as large. You just can compare the vertical scale here, which is completely different. And for the pi minus, the amplitude is consistent with zero. So again, we have a difference between k minus and pi minus. And the reason here is that only this favored and opposite fermentation mechanism can contribute in this case. Also, for the Collins, we have results for proton and antiproton. And indeed, these results are the first measurement of Collins asymmetries for proton and antiproton in SIDIS. Although the antiproton asymmetry is consistent with zero, the proton is not, and it is slightly negative, as you can see here.
Luciano, you have 2 minutes.
Yes, thank you. So, of course, in the interpretation of these results, one has to be careful because the Collins effect is a pure fragmentation process. So, too little is known today about this effect for spin-1 alpha hadron production. Let me go to the last results. So, the sub-bleeding twist sun phi s term, again for pi plus and pi minus, they are both positive and negative, respectively. So, again, we have a similar picture as the one we observed for the Collins symmetry. Again, we can learn more when we look in the three-dimensional, and we also see that locally, this amplitude, despite being a sub-bleeding twist, can be as large as 8–9%. And then, since this is a sub-bleeding twist term, it is also interesting to study the Q-square dependent. So again, we split each X bin into two Q-square regions, and we compare the two subsample. And as you can see here, there is a hint of a suppression at high Q-square, which are the black points. Then we have results for kaons, proton and antiproton, as before. So the pi plus and the k plus are essentially pretty similar. So the same kinematic behavior in the SIDIS regime. They are both small and positive. The k minus is negative and similar to the pi minus, whereas the results for the pi zero, proton, and antiproton are all consistent with zero. One last comment about this large Z region. So we have here for both pi plus and k plus a striking Z dependence, okay, which is consistent with the sin phi s amplitude we observed in exclusive pi plus production and we published back in 2010. So this drives me to the conclusion. The full collection of leading and subleading twist single and double spin asymmetries with a transversely polarized hydrogen target has now been published by Hermes based on an improved analysis and including proton and antiproton results, as well as three-dimensional binding and also extended to this large Z or semi-exclusive region.
Hello? Hello?
Can you hear me?
Yes, sorry, I was disconnected. Wow.
I was just shortly disconnected. Yeah, sorry. Yeah, let me try to show. Okay. Do you see again my slide?
Yes.
Okay, sorry for
hello, did we lose him again? Can anyone hear me?
We can hear you, but we cannot hear the speaker.
Okay, so we probably lost him again then. Oh, let's wait for a few seconds if we can actually reconnect, since we still have a few minutes. I guess not. I guess then I suggest we move on and address question later offline if you have for the speaker. So the next talk is from Yu-Hsiang for the compass Drell-Yan measure.
Yes.
Yeah. Yes. Go ahead.
Okay. Thank you. So today I want to present the measurement of the target spin dependence and the independent asymmetry in the dimuon production in the pion-nucleon collision and the compass experiment. And this talk will be presented on behalf of the compass collaboration. So first, in the recent year, our point of view for the platonic structure are extending from the one-dimensional to the multi-dimensional. So in the beginning, we are only looking for the consider the longitudinal momentum of the proton, which is the proton distribution functions. And now, if in the momentum tomography, we are extending to the 3D picture, which is the transverse momentum distribution, usually called TMDs. And another way is to extend in the spatial tomography, which is consider the transverse position of the protons. So this will end up with the generalized proton distribution, usually called GPDs. And if we be more ambitious, we combine both the transverse momentum and the transverse position, then this will end up with a 5D picture, which is the Wigner distribution. And today I want to only emphasize the TMDs. So in TMDs, PDFs, there are several functions, but if we consider this function are consider the transverse momentum of the proton and correlation between the spin of the proton and the spin of the nucleon. And if we try to sort according to the nucleon polarization and the individual polarization of the protons, we can end up with different PDF. And today I will only focus on the Born modus function and the Sivers functions. So in order to probe these TMDs, one of the tool is via Drell-Yan process. So we try to look into the Drell-Yan angular distributions. This can help us to probe the spin and the transverse momentum of the protons. So if we try to write down the leading order differential quotients for the single polarized Drell-Yan angular distributions, this can we can end up with the two terms. One is the spin independence terms, the other is the transverse spin dependence term. And so in these two terms, this will carry out a different asymmetry. But if we don't, if we just consider the spin independence terms, and this means the transverse spin dependence term will be vanished. And in this case, this leading order quotient will be simplified by only carried out by three asymmetries, which here I using the changing to using the traditional conventions, lambda, mu, nu. And I want to emphasize this quantity is actually the frame dependence quantity. So I will say that today's results will present using in the Collins-Sober frame. So not only the Drell-Yan process can probe these TMDs, but also the SIDIS can also get in these TMDs. So in the QCD framework, actually we can try to link between these two, the results coming from these two processes. So this will end up with the bring us to have like Bohr models, Sivers, transversality, and so on. They can both come obtain from the both process, and this will be another interesting part to test our TMD framework by these connections. So let's go back to talk about this unpolarized part. So this angular coefficient I just mentioned, this lambda mu nu, are usually often referred to as the unpolarized symmetries. So in the naive Drell-Yan models, actually, we know that the virtual photon was produced by the electromagnetic quark-antiquark annihilation. This means that due to the helicity conservations and also the fact that the spin of the quark is 1.5, so this will bring us to the extration should be proportional to the 1 plus cosine theta square. This means that the lambda should be equal to 1. And the mu and the nu should be equal to 0. But as we know that when we go to the higher energy, the gluon should be comes in, the QCD effect should be comes in. So this brings us the non-zero cosine true phi dependence. This tells us that the nu no longer to be 0, but still based on the QCD framework, between the lambda and the nu, there should be still conserve some relation. Here we call this is the lepton relation, which is 1 plus minus lambda should be equal to 2 nu. But actually from 1986, this lepton relation was found to be violated in the pion-induced Drell-Yan experiment. So in the bottom show you the results of the lambda mu nu and the lepton relation as function of dimuon transverse momentum QT. And the left-hand side plot carried out by the NA10, right-hand side carried out by the E615. And for each figure, the black point represent the measurement from the experiment, while the red and the blue point represent the PQCD calculation in the next leading order and the next leading order predictions. So as you can see, if we focus on the subfigure in the right bottom side, we see that the lepton reaction actually is violated in the large QT for both experiments. So this inconsistency will be is one of the puzzle in the past. But actually this, if you look more carefully, actually in terms of the PQCD calculation in the next leading order, this already bring us some sort of the violation of the lepton relation in the large QT. But the problem is the current prediction actually bring us the opposite sign for the lepton relation between the calculation and the experiment measurement. So in the right-hand side showing you the results from NA10 in the large QT go to the negative, but the PQCD calculation is positive. But actually this can be explained recently by introducing the non-predictive TMD Bohr models function. So this function actually is represent the correlation between the quark intrinsic transverse momentum and the transverse spin of the quark inside the unpolarized hadron. So these functions in the bottom is the showing you this function actually introduce the additional contribution of the nu as function of QT. So this can be after introduce these functions, so the results will be matched to the experimental measurement. And another interesting point is since we know that these TMD functions can be extracted by Drell-Yan and the SIDIS, but based on the picture of the QCD, we know in these two processes, the QCD gluon gauge link in the, for example, in the Drell-Yan is in the initial state, but in the SIDIS is in the final state interaction. So this brings us that the non-universality of the TMD functions. So for example, for the Sivers functions from the Drell-Yan process, should be with the sign change when we look into the Sivers function in the SIDIS. And this will be the fundamental prediction from the TMD framework of QCD. So this will be also the testing point ground for the whole TMD framework. And actually this one can be tested by compass experiment. So right now, let me try to introduce about the compass experiments. So compass experiment is a fixed target experiment and at CERN SPS node area. So we have many physics programs. So of course, we try to probe the nucleon spin and the platonic structure, and also the hadron spectroscopy, and of course the TMD functions, and even the pion structure. And our data taking starts from 2002, and the last round will be take place in the next year. And in the future, this will be superseded by the Amber experiment. So let me focus on the Drell-Yan program in the compass experiment. So in the Drell-Yan program, we are actually the first ever polarized Drell-Yan measurements in 2015 and 2018. We are trying to using 190 GeV pi minus spin, which deliver from the CERN SPS M2 beam line. And the most important component is we are preparing the transverse polarized ammonia target cells. And also, in addition, we have two more nucleon target. One is the aluminum, the other is the tungsten, which can lead us to carry out some nucleon dependence physics. So another important component is hadron absorber, which just put behind our polarized target. Since we are using the pi minus beam, so during the interaction, there will be a lot of the hadronic shower produced. And in order to prevent this hadronic shower to damage our spectrometer, we need to put this hadron absorber to stop all of the hadronic particle. And this absorber with the total length of the 240 centimeter, and it's actually incorporate with the 120 centimeter tungsten beam plug, and also the 7 centimeter aluminum target inside. So next is about the data analysis. So since by study the Drell-Yan process, in the final state, we are looking for the dimuon events. But dimuon event not only come from the Drell-Yan process, but also it was mixed up with from the other process like the OpenTron and the Jepside Cypran channel, and even the combinatorial background. So we are trying to using the Monte Carlo framework to try to extract, to separate each background and each source, and to understand our purity of the Drell-Yan process. So in the end, by this study, we end up with getting 96% purity of the Drell-Yan in the selective mass region. And another point to this Monte Carlo simulation is we have to use our Monte Carlo to estimate our acceptance for unpolarized symmetry extraction. So before that, we have to verify our Monte Carlo is really trustable or not. So we are trying to look into the data Monte Carlo comparison in each key kinematics distribution. So here I show you the comparison between the data in the Monte Carlo in the mass QT, XF, X1 and X2. And the data showing in the black point, Monte Carlo showing the blue histogram. So as you can see, we are reached the good data Monte Carlo agreement and for these key kinematics distributions. So this means right now we have confidence that we can proceed with the unpolarized asymmetry extraction. So here comes the results of the unpolarized asymmetry. So here we try to extract the lambda mu nu from left to right. Our results was is showing in the red point, and the other experiments is showing in the for Na10 is in the blue square, and E615 is in the green circle. So as you can see, we also try to compare with the D1N3LO calculation. So in the lambda extraction, we are more or less consistent with the other experiments. And let's focus on the new extraction. In the new extraction as function of Qt at large Qt, our preliminary result actually tend to deviate from the PQCD calculation, which is also consistent with the old pion-induced experiment, pion-induced Drell-Yan experiment. And this may indicate the presence of the non-zero TMD Bohr models effect. And currently, these preliminary results are based on about 70% of the compass tungsten data collected in 2018. So in the future, we hope we can use in the full statistic to bring out the new results.
You have 2 minutes.
Okay, thank you. So another point I want to highlight is about the results of the lambda variation. So by combining the lambda and the new extraction, we get here show you the lambda violation as function of Qt. So as you can see, our preliminary results in the large Qt also showing the violation of the lambda variation, which is consistent with the other experiments. And so this is our current situations. So the final point is about the Sivers asymmetry in the Drell-Yan process. So in 2017, we already, Compass already published the first results of the Sivers asymmetry in the Drell-Yan process, and we obtained the sign change of the Sivers function. And recently, there's preliminary results which combine with the both 2015 data and the part of 2018's data, and we are still keep in favor of the sign change. Currently, this analysis combined with the full statistic of 2 years are still ongoing. So let me bring you the summary. So Compass studied the beam and the platonic structure of the nucleon with the SIDIS and the Drell-Yan channel by using the muon beam and the pion beam, which interact with the different polarized and the unpolarized targets. And in 2017, Compass have published the results of Sivers asymmetry from the first ever polarized Drell-Yan measurement. And right now, the preliminary results of the Drell-Yan angular distribution from Compass tungsten data may indicate the presence of the TMD Bohr model function. And currently, there's still various ongoing analyses like causation, ENC effect, polarization, dependence asymmetry, polarization independence asymmetry, and the drape side asymmetry, and so on. So that's all from my side. Thank you for your attention.
Thank you very much for the nice summary. Now we have a few minutes for discussion and question. If you have a question, please raise your hand. Alexey?
Yeah, I have a side question. In measurement of different angular modulations, so you also probably measure unpolarized cross-section, yes? To which you normalize. So do you plan to release it? I mean, totally unpolarized cross-section, so this coefficient in front of 1 in this formula?
For the causation, so for the Drell-Yan causation, this is also the ongoing analysis. So this is also the plan. Yeah.
Okay. Thank you.
Okay. Another question, comment for Yu-Hsiang? Actually, I have a question. When I look at your mass distribution, I think you may have also some statistics for looking at the epsilon. Do you actually have enough statistics to look at it, or have you tried to look at the epsilon as well?
Actually, we also try to introduce the epsilon component during this fitting. But actually, yeah, you are right. Our statistics actually not enough to carry out this. So in the end, we just cut out this region. Yes.
Okay. All right. I guess there's no more question then. Let's thank speaker again.
Thank you.
Okay. Our next speaker, Alexey.
Yes, one moment. Do you see my screen?
Yes, you can see. You can go ahead. I will also give you a 2 minutes warning.
Okay, thank you. So thank you very much for invitation to DIS. I would like to present our recent work about extraction of the Sivers function, which was done at N3LO from SIDIS, Drell-Yan, and W and Z data. This work was done in collaboration with Martin Berry and Alexey Prokudin. So yeah, so the results are published in these two papers. And the main part of results with a lot of details are given in this recent publication. So I will not go into detailed description what is Sivers function, what are TMDs, because we have seen it already on previous talks. But I will go into some details about structure of the theory of TMD factorization for Sivers asymmetry. So here is a formula which comes out from TMD factorization for Sivers asymmetry at leading power. So in principle, I should be able to write here some power corrections in 1 over Q and PTs. And this formula is actually quite curious. First of all, many factors cancels because we take a ratio. And probably what is important is that hard coefficient cancels completely, which is a bit unusual for such kind of formulas. And if I go to dissect it, so we'll find here rich structure. So each integral in denominator and numerator is a convolution of 3 non-perturbative functions. So by this blue box, I denote a TMD evolution factor, which is generally non-perturbative, and it's a non-independent function. And by red, I mark unpolarized functions. For example, unpolarized fragmentation, TMD fragmentation, unpolarized TMD partner distribution function, and the green actually is the one which we going to extract, so it's a Sivers function. So nicely, already from previous extractions, we know all unpolarized ingredients, so unpolarized functions, and also an non-perturbative evolution. And for this input, we use a SV19 feed, which is a feed of SIDIS and Drell-Yan simultaneously, which was done in this paper. Okay, and the numerics, so always integral convolutions, so they are done by Artemida. What is the role of perturbation theory in that formula if hard coefficient is cancelled? Because you remember I told that hard coefficient disappears. So yeah, let me again, so it's kind of complicated. So let me look into each term separately. So first of all, of course, we have kind of standard perturbation input. So it's hard coefficient function, which is cancelled in the end, and of course, evolution. So evolution with respect to mu. So both these terms we took at N3LO, which also include full loop gamma cusp. But in addition, for these TMD distributions and for non-perturbative part, we use a small b matching. So despite this function fully non-perturbative, if you go to very small values of b, you can use operator product expansion and match them at small b to collinear distributions or just to perturbation theory. So in case of unpolarized distributions, we used two-loop matching, and for evolution, we used three-loop matching. It maybe looks strange that we actually use, say, two-loop evolution here and three-loop, two-loop matching here and three-loop computation here, and it looks like kind of inconsistency. However, it is not, because in zeta prescription is specially built such that you can use, you can really decorrelate non-perturbative functions from hard coefficient function. So you may think about it as a fixed scale in DIS. So you evolve your TMD distribution to some particular scale where you define them completely independently of evolution. So such approach will be not possible in resummation-like schemes like CSS scheme. So what about Sivers function? So for Sivers function, we do not use any small b matching, and it's also consistent with the fact that we use free loop evolution. Why we don't do it? Just because Sivers function, a small b, match to at least three collinear distributions, which are completely unknown. So there is no practical reason to actually use any small b matching. So as I told, hard coefficient function cancels, but doesn't mean that we don't have any evolution, because we still have evolution with respect to rapidity. So this factor here, so CV cancels, but we still have evolution with respect to Q here inside of our non-perturbative factor, and it looks like that. So this evolution is actually gives you very fast drop at small q, but then you have more or less stable cross section. And if you start to go from order to order, you observe a very perfect convergence. So from green line, which is leading order, to black line, which is free loop evolution. So you see it's indeed very nicely convergent. So this is a presentation for particular beam of Hermes, just for reference. Okay. That is part comes from theory. What about data? So to be able to apply TMD factorization, we really have to consider small qt. And qt is just qt in Drell-Yan or pt divided by z in case of SIDIS. So qt should be smaller than something like 0.3 q. And it's, of course, cuts out huge amount of data if you look at the global pool of SIDIS data, but that's a surprise of application of TMD factorization. So here, with a scatter plot of points, of all points which we have in our analysis, in total there are 76 points, so most part of SIDIS and 13 points from Drell-Yan. And actually, really main part of points, about 50, comes from recent Hermes 3D analysis, which was just presented 2 talks ago. So if we talk about Drell-Yan, so actually all points of Drell-Yan are valid TMD points except one. I just specially plotted here to demonstrate our strategy of data cut, because if you look at these points, this last point is collected at very large bin in QT. You see from 1 to 5, and that's why it is not TMD point, because it's actually generally has QT of order of Q. That's why it is not described by TMD factorization. And indeed, so if you try to describe it, we get very huge discrepancy mainly due to unpolarized cross section. Okay, so and then we have that amount of points, and this is our answers for Sivers function. So it has generically 2 parts, one for non-perturbative KT dependence and now for non-perturbative X dependence. So PT dependence is inherited from unpolarized feed, so it has the same structure. It has 3 parameters and they're common for all flavors. And for X dependence, we have also 3 parameters, so normalization, X in power beta, and this node position. However, of course, data is not sufficient to fix all of these parameters. That's why we fix them partially. For example, for C and S quark, we equalize the power of beta and also put this node parameter to 0. And also in some very initial models, we had this 1 minus X in power alpha, such that we can presumably could control behavior at at large X. But we found that the data just cannot fix this parameter at all. So generally, you can put any number from 0 to 5, and you'll be still able to describe data. So that's why in the end of the day, we just fix it by hands equal to 1. Okay, so so in the end of the day, we have 12 parameters, 76 points. And if we try to describe them, first of all, what we observe that large errors on data results into large errors, large uncertainties on our extraction. And also this uncertainty in distribution of parameters is extremely asymmetric. So if we try to, so for example, show replicas, this is our typical distribution. So with some value of Sivers function, particular x and b point, and you see, so distribution of this replica is really symmetric. So that's why in the end we present our uncertainty just as a collection of all replicas, and we produce 300 replicas. And actually, we also computed additionally replicas due to, sorry, uncertainty due to unpolarized input. And as you can see, so it is sizable, and say it will play actually a role, and I hope in nearest future. But for a moment, in comparison to experimental uncertainty, it is almost negligible. So it's something like 5 times smaller. So that's why we just drop it. And the all following, I just present uncertainty due to data. So the fit is the result of that value of chi square. And what is important, actually, we perform several fits. And first of all, we just fit only SIDIS and check, is the fit of only SIDIS capable to describe the Drell-Yan data? Because it is known that many groups faced some problems of describing Drell-Yan Sivers asymmetry. However, we do not see such a serious problem. So if we just fit SIDIS, you see chi square of Drell-Yan, which is not fitted. So it's something like 1.2 for 13 points. So if we fit them together, so of course it goes down, but in fact it's just a fine tuning of our parameterization, which incorporates Drell-Yan. So value of chi square is of course very small, but I remind you that we have very large error bars on data points, as I will show on next slide. So here some just 2 snapshots of this 70 plus something points. On left, this is a typical representative of Hermes 3-dimensional binning. So black points are points which were included in the fit. So that's a points which survived in B-cut, while open points are the points which were not included in the fit. And you see that in principle, actually, we can describe more data than were included, which is probably related to the fact that in ratio, a lot of power corrections cancels. And that's why, in principle, you could try to apply TMD factorization higher. So we made a special check, and actually we find out that this data cut rule could be pushed up to 0.4 Q in SIDIS. So on the right, you can see this famous Sivers asymmetry measured in W and Z production. And again, so we included only PT bins, which are black points, and didn't include Y bins, but they both equally nice described given this huge error bars. Oops. Yeah. So this is the result. So that's our extracted Sivers function as a 3-dimensional plot in B space. And what you immediately realize that actually, indeed, we have very large uncertainty. So that's what we have at the current data. And another feature of our extraction that we observe that our U quark Sivers function is not sign definite. So here, if you look at values of very large x, okay, actually not that large, I will show on that other plots, it's up to 0.1 almost. So it's changed sign at some moment. In principle, it of course can be hidden behind these large error bars, but since anyway we observe that central lines prefer to change this sign. So that's why it would be very interesting to look, say, at JLab data, which we will measure high X regime, so that we can really identify. So is it happened or not?
You have 2 minutes.
Oh. Okay, so then I'll start to do it a bit faster. Yeah, so of course we also made a lot of additional studies because extraction is just a first step. I will highlight some of them. In particular, I would like to highlight extraction of Yu-Hsiang function. So Yu-Hsiang function is a function to which Sivers function match its small b. So it is some generic twist-free. So it's a part of twist-free function. So if you look at a general twist-free function, so which is function of two variables, so Yu-Hsiang function is just a particular value at this red band. And of course, it cannot be just extract like that because you have to fit it simultaneously and take into account all the evolution, which of course live in all the two-dimensional plane. So, and we use the following strategy. So first of all, we took it this formula. We fix mu such that we can kill the most complicated part. So which mix together different parts of our phase space. Then we invert this formula perturbatively. We get something like this. Took small b such that we can apply that formula and simultaneously that mu is not that large, and we get that expression, that result. So probably it is most accurate extraction of Yu-Hsiang function which happened so far, and it's give us that large band which is shown here by blue. So in principle, we also have a mixture of gluons which we cannot extract currently, so it's just parameterized by such a value, and it's of course gives even larger band which is shown by brown. So and here you can see that change of sign for U quark which I previously mentioned. So this is the same Yu-Hsiang function for S and C quark, and here what is most notable that indeed so huge error bands actually prevent to see any reasonable information. Okay, that's one of final picture which I'm going to show. So this tomographic picture of hadron. So it comes from momentum space density, which is combination of unpolarized function and Sivers function. And yeah, for U quark and D quark. And this is a particular slice at x equal to 0.1 at 2 GeV. And you can see it's this slight asymmetry. So this cross shows the center of hadron momentum space. And indeed, we can see some small asymmetry due to Sivers effect. Unfortunately, so as I told, errors are very large. That's why this distribution of colors actually try to represent these errors. So it's not very well pronounced so far. Maybe it is more convenient to look at this picture on different sides. So since it's actually absolutely symmetric in vertical x, so let me make a slice at different axes. So as you can see, at small, so vertical x here is x, horizontal is asymmetry in KT. So as you can see, at small x, there is no asymmetry at all because unpolarized function is much bigger than Sivers one. But once you go to larger x, it became asymmetric. Okay, so since I don't have more time, so I come to my conclusion. So I presented to you the extraction of Sivers function from joint fit of SIDIS and Drell-Yan data. It was done at N3LO in data prescription. We used conservative cut for data, and maybe because of that, we have quite large error bars, quite large uncertainty of our extraction. There are also many supplementary studies which I was not able to present because short of time, so you can find them in publication. Results of its extraction are available publicly, so you can either download them as a part of Artemida or in TMD lib. These are given by set BPV20. So thank you for your attention.
Thank you. Any question, comment? We have a few minutes. Carlo?
Hi, can you hear me?
Yes.
Yes.
All right. Hi, Alexey. Very nice talk. Just a curiosity. Since you showed the not definite sign for the U quark Sivers function, I was wondering whether you tried to not allow in your parameterization to have a node, but to allow the large X parameter behavior not to be 1, but some other value, and whether you found whether you did it and whether you found any solution.
Yeah, I understood the question. So yes, at the initial stage, we actually played with a lot of different models. And kind of our main aim was to reduce number of parameters, of course, because we have not too many points and not too many points to fit. So status is like this. So as I told, for this large X behavior, we can use practically any value. Say we can put 2 or 3. It also works. for this, but actually uses this node here really decrease chi square. So if we, for example, fix with epsilon equal to 0 in our parameterization, so we still have reasonable chi square. That's true, something like 1.2, for example. But once we introduce it, it immediately drops from 1.2 to something like 0.8. So of course, you can say that statistically it's not that valid, true, but it helps to fit.
Oh, okay, thanks. No, it's very interesting. I mean, there's nothing that prevents the Sivers function not to have a node. So it was just a technical curiosity. Thank you very much.
Anna, can you make the quick question?
Thank you. Hi, Alexey. I would like to go back to the selection of data you did. So you say that the TMD factorization is valid only at Qt over Q much smaller than 1.
Mm-hmm.
Then I do not understand the cut at 0.3 because it's not much smaller than 1. And also I would like you comment better the fact that you can reproduce also the data with Qt over Q larger, even if not included in the fit.
Yeah, okay.
I do not understand. It seems that in fact factorization works even at larger Qt.
Okay, so first of all, let's about this 0.3. So okay, in principle, 0.3 is much smaller than 1. That is correct. At Vevo studies, that showed that in principle you can use Qt over Q up to say 0.25, which is typical cut. Why so? Because power corrections comes in Qt squared divided by Q squared. So if you use 0.3, it is 0.09. So something like 10% correction. Actually, we use that slightly higher value because if you use it at 0.25, we throw away too many points. Then they just have nothing to fit, in fact. So that's on my side. On our side, as I told, so in principle, we just use that cut and then try to describe other points. Yes, like here. So for example, here you have this Qt over Q, something like 0.4 for this pin. And we see that we can describe that data. Why it happens, it's probably just because cross-section is smooth enough. And when once you continue some smooth function, you are able to describe other points. But generally speaking, factorization there should not work. So it's not reliable to use factorization formula. You can just check it and it works. So does that answer your question?
This is a good news. Thank you very much.
Yeah, just one short comment about it. This example of pion Drell-Yan. So I put it for special reason because so it's known that this prolongation factorization region works better for smaller Q. Once you go to larger Q, like in Drell-Yan, so actually this limit becomes very steep, because it appears that TMD cross-section in unpolarized regime at some moment just goes negative for large Q, for a very large Qt where it's not valid. And then your asymmetry becomes infinity.
All right, thank you for the nice discussion. I think we should move on. Thank you again for the nice talk. The next speaker is Carlo.
Yes, can you hear me?
Yeah, please go ahead, sharing your slides.
All right, can you see my slides?
Yep.
Okay. Now?
Yeah, it's full screen.
All right. So, may I start?
Yes, go ahead.
All right. First of all, thanks to the organizers for allowing me to present our work here. I will talk about the reweighting of the quark-Sivers function using the recently published StarJet data. This work has been done in collaboration with Elena Boglione, Umberto D'Alesio, Osvaldo Gonzalez, Francesco Murgia, and Alexei Prokudin, and has been published recently in Physics Letters B. So to start with, I don't think I will say nothing new about Sivers function. We've heard a lot about it, but let me remind you some features of it. It is a genuine TMD distribution and describes the correlation that exists between the transverse polarization of a proton and the intrinsic transverse momentum of unpolarized partons inside the proton. Usually, we refer to the Sivers function either at this object in the Torino-Cagliari notation or at this object in the Amsterdam notation, and these two quantities in red if you equalize them, this is one of the Trento conventions. As we have seen, the Sivers function can be extracted from SIDIS azimuthal asymmetries, especially this specific sen phi h minus phi s modulation that is a ratio of two structure functions and is proportional to a convolution in which we are directly probing the quark Sivers function. It is also non-universal in the sense that due to the different gauge structure in terms of Wilson lines that we probe in the Drell-Yan and in the SIDIS process, we expect that the Sivers function that we probe in the Drell-Yan has an opposite sign with respect to the one that we probe in SIDIS. In the following, in the model that we will use to describe inclusive jet production in polarized proton-proton collisions, the so-called generalized Parton model, we describe the single spin asymmetries in terms of the Sivers effect. So to give you more details about the formalism, what is the generalized Parton model? It's essentially a model in which a factorized formulation in terms of transverse momentum-dependent distributions and fragmentation function is assumed as a starting point. Recently, a core gauge invariant formulation of this model was developed by Gamber and Kang in this paper for quarks and then extended in the case of gluons in this paper. And in this extension, the inclusion of initial and final state interaction is done through a one gluon exchange approximation, and the process dependence of the Sivers function is recovered. When we want to describe the single spin asymmetry measured in inclusive jet production in polarized proton-proton collision, we consider this observable. That is essentially a ratio of the difference and the sum of the polarized cross-section when we reverse the sign of the polarization. And essentially, we can write in the core gauge invariant generalized Parton model the numerator of this asymmetry in this way as a convolution of the Sivers function, the unpolarized PDF, and hadronic cross-sections that are particular because here, essentially, how the CGI GPM works is that we consider still the Sivers function extracted by SIDIS, and we recover the process dependence by modifying the Partonic cross-section through the one gluon exchange approximation and calculating different new color factors. The denominator of the asymmetry is common between the CGI and the GPM, and it's written in terms of unpolarized TMDs, unpolarized hard factors, and essentially, if we want to write the numerator in the case of GPM, we take this expression and we substitute the modified hard factors with the ones not modified, and we get the expression in the GPM case. So in our work, we use the reweighting method. Reweighting is a well-established technique in the context of collinear PDF fits. It allows to assess the impact of new data sets on existing extractions, avoiding performing a new global fit that can be quite computationally expensive, for example. It has been used both in the Bayesian framework and in the Hessian approach. What we will do here is to apply for the first time the Bayesian reweighting to a TMD density, the quark Sivers function, that we adopt, and we adopt the parameterization from this paper in 2018, in which we parameterized the Sivers function for up and down quark in terms of its first moment and factorizing the X and K pair dependence with a flavor independent Gaussian width. And essentially, we could parameterize the first moment of the Sivers function in terms of a normalization and a large X behavior, large X parameter. To be more general now, what is the reweighting method that we have used? Consider in general a model for a TMD that depends on a certain amount of parameters. And we have a probability distribution for all these parameters. And of course, if no prior knowledge exists, the probability distribution, the prior probability distribution is flat. Then we take a set of data and we can define, as usual, a chi-square function that depends on the data and on the parameters and on the data, and with a correlation matrix. And if only, of course, only uncorrelated uncertainties are known, we recover the usual quadratic form. Then we minimize this chi-square and we find the best fit with associated minimum chi-square 0. And we build the uncertainty on our extraction with some parameter sets that respect a criterion on the chi-square within a certain tolerance. And again, we calculate the chi-square for every parameter, and we check whether it's in this inside this interval that depends on the delta chi-square. In our case, since we have 5 parameters and we select the 2 sigma confidence level, the value of the delta chi-square is this one. In particular, we produce 2 × 10⁵ sets adopting a Markov chain Monte Carlo procedure with Metropolis Hastings algorithm. Now, when we want to see the impact of data, we calculate, of course, the posterior density through Bayes' theorem. And essentially, we take the likelihood, we multiply it by the priors, we normalize for the evidence, and we have the posterior density for the parameters given the data. If we consider this product of the likelihood and of this differential volume dy as the probability to find this new data confining this differential volume around y, we are brought to define weights in this way, in this exponential form that depends on the chi-square for every parameter sets and are normalized to 1. And with these weights, we can calculate expectation values and variances for an observable in a symmetric way with these 2 expression in a discretized expression. But in our work, we have extended the calculation to asymmetric errors using the RV discrete function of Python SciPy model. And in what we will present the median as central value and the uncertainty at 2 sigma confidence level. Of course, when new data comes into play, new data will change the weights so that we can calculate a new chi-square, the weights will change, and so also the posteriors will change. And so in view of this, we apply this procedure to the quark-Sivers function with star data. This star data has been published recently in this paper and has been collected in 18 points at 2 different energies, 200 and 500 GeVs. It's essentially a data set for electromagnetic jets. And for this reason, we have selected the set of data with photon multiplicity larger than 2 to be sure that we are not contaminated by other processes like single photon or isolated pi0 production. Let me stress that this data is quite important because it's covering a wide region in XF that is complementary to SIDIS, because in the generalized Parton model, when we calculate the cross-section, we integrate over x the longitudinal momentum fraction starting from XF to 1. And essentially, we are covering a region in X that is not covered by SIDIS data, as also Alexey had showed in the previous talk. So let's start first comparing predictions based on the extractions from SIDIS data only, the ones from our paper, both in the GPM on the left or in the CGI on the right. And we see that both descriptions within large uncertainty are describing the data. But then when we apply the reweighting method, we see that the reweighted curves for both models are show reduced uncertainties. To be essentially, we see here this reduction of uncertainty, and we can see how the posterior changes. Here, I present the comparison between the priors from SIDIS and the posteriors, calculating when reweighting also with the jet data by star. First of all, we can see that the flavor-independent Gaussian width here in this lower left corner does not change very much. And this is also a sign that in general, in the asymmetries, evolution effects are milded. the beta Q parameters that govern the large X behavior change differently when applying the generalized Parton model or the core gauge invariant version. And this is due to the fact that in the CGI, we have a different combination of partonic cross-section due to different core factors. And we see also that the normalization, while for the normalization for the up doesn't change very much, it's quite similar. We see that the normalization for the down quark is smaller in size. But combined with, for example, in the CGI case, combined with the information on the beta parameters, we can conclude that it is true that the d-quark Sivers function in the CGI is suppressed in size, but is also less suppressed in the large X region. And essentially, comparing the chi-square after the reweighting for the two models using this value for the number of parameters, 220 parameters from the SIDIS extraction plus these 18 points for the SIDIS and 18 points for the jet, there seemed to be favor for the GPM, but this difference is not enough to disentangle between these two approaches. And indeed, to look at the extracted function on the upper panels, you see the first moment for the up quark Sivers function, and on the lower panels, the one for the down quark. And this is the extraction from semi-inclusive DAS only. And then when we apply the reweighting, we see again a reduction of uncertainty for both U and D, both in the GPM and in the CGI GPM. And here you can clearly see what I said before. The Sivers function for the CGI, the d-quark Sivers function is reduced in size, but also it's less suppressed at large X. And to see the behavior of the Sivers function after the reweighting at large X, let me show the ratio of...
you have 2 minutes.
Yes, thanks. Let me show the ratio to the central value, I mean, the self-normalized functions. Again, here you can clearly see that at large X, both for up and down, you can see a very large uncertainty at large X in a region that is not covered by the SIDIS data. Essentially, the SIDIS data covers up to 0.3 roughly. And you can clearly see that applying the reweighting procedure and using star data allows us to constrain the Sivers function at large X in a complementary region to SIDIS data. So to conclude, we applied for the first time reweighting procedure to a TMD density, the quark Sivers function, and in doing so, we have also extended the Bayesian reweighting to the case of asymmetric uncertainties. We have shown that this new star data allows to improve and extend the knowledge on the Sivers function at large X, and essentially in a region complementary to SIDIS data. The natural extension of this study would be global analysis, including also single spin asymmetries for inclusive pion production, so that we could, for example, simultaneously reweight not only the Sivers function, but also the TMD transversity and the TMD fragmentation coordinates fragmentation functions. But in general, we expect that forthcoming measurements from COMPASS, from JLab, and from the EAC will play a crucial role in pinning down these TMD functions and in unraveling the nucleon structure in its full complexity. Thank you for the attention.
Thank you. Any question, comment? Please raise your hand. Yes, Yanis, go ahead.
Yeah, I have. Hi, Carlo. I have a quick naive question. In the form of the weights that you had, I was wondering where that comes from. Why is it pure Gaussian? Is that the rest of the terms go away through the measure or something like that?
So I didn't put. Let me go back one few slides. If you look in this reference by Nobuo Sato, Josh Owens, and Eric Prosper, they explain that essentially, depending on the likelihood that you take, whether you take where you consider essentially a likelihood that a probability to find new data confined in a differential volume dy around y, or if you take a likelihood that it's based on the chi-square, you have a different expression for the weights. If you look, for example, an NPDF reweighting method that brings two different weights. And this all depends on the form of the likelihood that you adopt.
I see. All right, thanks a lot.
You're welcome, thanks.
Okay, any other questions, comments? Thank you again for the nice talk.
Thanks.
So next is from Ishara.
Hello?
Yes,
Can you hear me?
Yes.
Okay, let me share my screen. Do you see my screen?
Yes.
Okay, let me put it in the full screen. Okay.
Yep.
Okay. Yeah. May I start? Or?
Yes. Go ahead.
Okay. Good afternoon, everyone. So I'm Ishara Fernando from University of Virginia. So I'm going to give a very brief, preliminary results on the current ongoing work on Sivers extraction with neural network. So the transverse momentum dependent pattern distribution functions, or TMDPDs, are a key tool or a probe to investigate about the three-dimensional structure of the nucleon, which was originally proposed by Collins and Supper and Sterman. So these TMDPDs can be extracted from the processes that are corresponding to multiple kinematic scales, such as Drell-Yan, semi-inclusive deep-inelastic scattering, or SIDIS, and electron-positron annihilation. Because the cross-sections measured from these processes are sensitive to the transverse momentum of the quarks and gluons, or in general partons, especially the magnitude of the transverse momentum corresponds to non-negligible and non-perturbative interactions. So here is a cartoon of the Sivers process, the incoming lepton and the nucleon plane and the hadron plane and all the kinematics and also the angles, azimuthal angles are mentioned here. So the differential cross-section can be parameterized as proportional to the summation of TMDPDFs and the fragmentation functions for all the quark flavors in general. And the other kinematical terms, variables, can be factorized separately, and the high order terms will be order k per 2 divided by the q, the scaling. And there are 8 TMDPDFs that are at the leading order of the twist expansion, which can be classified by the quark polarization and the nucleon polarization. Among these 8 TMDPDFs, this Sivers function is the main focus of this work, which describes the distribution of the unpolarized quarks inside the transversely polarized nucleon through a correlation between quark transverse momentum and the nucleon transverse spin. So when the target is polarized, the distribution of quarks and quarks can be parameterized with 2 terms, as mentioned here. And basically the second term is a modulation of the distribution where the quarks tend to move to any direction. And here are the some indications or for the Sivers asymmetry for non-zero indication by the Hermes data and also the E0704 experiment. And for the SIDIS process, the single spin asymmetry can be written in terms of the difference between the cross sections of the possible polarizations and divided by the summation, which is the normalization for that. And from the approach by Anselmino and collaborations. So this was explicitly parameterized by these kinematical variables and the second term, which contains the summation of the fragmentation functions and the PDFs, convoluted by this NQ, which handles the quarks distribution term, divided by without that, the summation of without that. And yeah, so these are this k squared and the k perp and the p perp. So these parameters are fixed by in the I approach by fitting into multiplicities from the Hermes data, and we use the same fixing parameters, like fixing constants. And this yeah, so these are fragmentation functions for quark flavor Q and the hadron corresponding to H. And this can be simplified, like written in terms of basically multiplication of A0, which carries all these kinematical terms, and the second term which handles the numerator and the denominator of the convoluted PDFs and the fragmentation functions and this NQ. And the quarks, so this NQ was parameterized as this, and the C quarks was just considered as like this in this framework. So in the current work that we are doing, so these are the differences corresponding to the work by Anselmino and collaborations. So we use the input, the same PDFs, the formal LHA PDFs, CTEC X6L, and they use the DSS formalism for the fragmentation functions, whereas we are using NNFF PDF sets for the fragmentation functions for different hadrons produced in the SIDIS process. And in addition to considering 9 parameters in the Anselmino work, we are actually letting the strange quarks into the play. So we have 13 parameters in the fitting framework. And thanks to Luciano and Bakur for providing the data sets for Hermes, Compass, and especially the new data set from Hermes to 2020 day, like the very recent publication. And the fitting procedures are basically 2 procedures that we tried. So first it's like iMinuit, the Python supported version for the Minuit, and also parallelly we check that with the Python SciPy optimized curve fit. So they produce basically the same results. And in addition to that, so this is the new approach for using the neural network. So that's basically our methodology. Okay, so let's look at some results to only fitting into the Hermes 2009 data. And here is the chi-squared budget, and we got the total chi-squared per degree of freedom as 1.84. And here all the hadrons and their corresponding dependencies, so we included all the data. And the fitted parameters are here. And considering 95% confidence interval, so we you can see the theory, the bands that we obtain from the fitted coefficients for the pi plus and k plus and pi 0. So and then did the same thing only to the Hermes 2020 data, which is the new data set actually. So then we were able to get the chi-squared per degree of freedom of 1.477. And here are the chi-squared per degree of freedom for each dependencies for a given hadron in the SIDIS process. So we can see that most of them fit very well, and then some stretches coming from the K plus here. And if we look at the behavior, the extracted the bands from the fitted coefficient. So this is the pi plus and this is the pi 0. So, and then we implemented the neural network approach. So here is the schematic of our framework. So we have the parameterization, and the kinematics are x, z, and pht. And we use the PDF set the same as what we did for the conventional fitting CTEC 6L, and the fragmentation functions are from neural net FF10 next to leading order. And here, for each flavor, we are implementing 6 neural networks for each flavor, which each one is consist of 2 dense layers and 32 neurons or nodes. And they are convoluted with the PDF and the fragmentation functions and giving us the numerator of this expression. And then the denominator is basically the convolution between the fragmentation functions and the PDFs. this set, and the A0 is just calculated by the kinematics. And then the asymmetry, the Sivers asymmetry was trained against that only using the 2009 data at the first stage. So if we do the fitting using the neural networks only to the Hermes 2009 data, so you can see the total chi-squared per degree of freedom has improved. And also the dependencies with respect to the corresponding hadrons. And pretty much we were able to produce the hadron, the Sivers asymmetry for hadrons, the bands, like without doing any parameterization for the NQ. So so here is basically the neural network for each quark flavor. And using the trained neural network parameters like the neural networks, we predicted the Hermes 2020 Sivers asymmetries using the trained network, and compared against the real experimental data for the Hermes 2020. So you can see here the chi-squared, calculated chi-squared per degree of freedom. So it's little large. So we are this is just preliminary. So we are still starting to investigating on this. So, and also the neural nets are only trained to one data set. So we are working on the global fits. So when we predicted the Hermes 2020, so you can see the bands corresponding to the kinematics of the 2020 data training by the 2009. And okay, so considering the conventional fit results, not using the neural networks, so using those fitted coefficients, we extracted how the Sivers function looks like. So using this parameterization, you can deduce the Sivers function and multiplied by the x. So that would the additional advantage here from our approach is like, so we have UDS quark Sivers functions as well as the anti-quark Sivers function. So the U bar, D bar, and S bar. So of course the bands are a bit large here because we only fit to one data set. So we are hoping to improve that. And these plots are for fixed x, which is 0.1, and fixed q squared 2.4. And the x-axis here is the transverse momentum of the quarks, and the p squared and k squared also fixed to the same numbers that Anselmo did. And using the neural trained neural network for 2009 Hermes data. So here are the Sivers functions obtained from the neural network approach. So basically they are consistent, kind of consistent to each other for the quarks and for the anti-quarks. So we, as I said before, so which is just trained by only one single data set. So hope to improve that. And also I wanted to say about the getting information about the C-quark Sivers function, so which is very important. And the SpinQuest experiment, or E1039 experiment at Fermilab, is going to be the first doing the first measurements of the C-quark Sivers function. And here at Fermilab, using a polarized target from Los Alamos National Lab and the University of Virginia. And here we will get 120 GeV proton beam and producing mu plus mu minus pair within the invariant mass range of 4 to 9 GeV. And the kinematical range for the target and the beam is mentioned here. So basically the X beam is ranging from 0.3 to around 0.9. And the X target, which is the important part of here, is 0.1 to 0.5 here. So please stay tuned for these results. And yeah, so this is the discussion and the future work on the ongoing work. Fits to individual datasets can be implemented with inclusion of the strange quark contributions, and also with the neural network. And we are performing the global fits. That's kind of ongoing work. And also hyperparameter search for the optimized neural network. So we are optimizing the hyperparameters for the neural network to produce promising kind of results, and exploring different neural network architectures to handle the different quark flavors. So, and also training with more LHA PDF sets. So right now we are using only the CTEX6L LHA PDF sets, which would let us to handle all the ambiguity at a very low X. So that's another goal. And then investigating towards Sivers asymmetry extraction, also from the combining the Drell-Yan and without considering the sign flip for the Sivers function. So that's coming up. Thank you very much.
All right, thank you. Now open for question, Alexey.
I have a question regarding selection of collinear input. So you used NNFF as a collinear input for fragmentation function. Did you try it, say, DSS?
DSS? No.
The reason I'm asking, so because when we made a study of unpolarized SIDIS, we actually found that the result is quite strongly dependent on input fragmentation function, and particularly in our case, NNFF was the worst. I mean, seriously worse. Say DSS and GEM, something like that. They were reasonably nice and agree with each other, but NNFF was seriously distinguished from them. So I just was wondering, so did you try another case? Okay.
Yeah, so we wanted to investigate that also because the implementation of the DSS and yeah, so we need to we are investigating on that, and it's a little strange why they are so different, and maybe if you can comment on that, like
okay,
why they
I'm not actually, it is known that they are really different. So just if you plot them, you will see that the shape of functions are quite different. And if I correctly understood, so it's because this NNFF 10 was extracted mainly from A plus and minus, and all other cells took into account some SIDIS data.
Yeah, okay. So but
it should be corrected by someone maybe.
Yeah, and also I should mention that we tried with the JAM. So the JAM has the segmentation functions too. So we tried with that also. So then, but eventually we realized that maybe NNFF10 would be better. Okay. So yeah, maybe we should train with all the available fragmentation functions and also including the DSS.
Yeah, so just again commented. So look in our SV19 paper, so we have special discussion about it there. If you're interested.
Thank you so much.
You're welcome. Thank you.
All right, I see actually many hand raised, but let's go in order. Next, April.
Yes, hi. Maybe you said this, but why is do you know why the fit to K plus is like so much worse than all the others in terms of the chi-squared?
Yeah, so you mean the conventional fitting?
Like,
and
especially with the 2020 data set, it was like 7 compared to like the rest. Yeah.
7.
K plus with the Z dependence, it's like a chi-squared of 6.3, and the rest are like a lot lower than that.
So that maybe, so that the suspect would be the Z dependence. Yeah, there may be some stretching there. So the reason regarding that, I don't know. So we need to investigate that. This is just like a preliminary fit results from there. So there may be some stretching with the strange quark contribution because comparing to the implementation of the Anselminos framework, they have not included the strange quark parameters, but we are including here. And for the kaons, I think there should be a big contribution from the strange quark, and that's why, okay. Yeah, maybe that's why. Yeah.
Okay, thank you.
Thanks.
We have more, but we should probably move on for now, and perhaps bring the discussion on the chat or after the session, okay. Just to move on the in schedule. Okay. But thank you again for the nice talk.
Thank you. You're welcome.
All right. Next is Francesco.
Hello, can you hear me?
Yes.
Let me share the screen. Can you see slides?
Yes, looks good.
Okay, thanks. Let me start. Before to present results, I would like to thank you, the organizers and the conveners, for the opportunity to speak at these nice conferences. And I will discuss some progresses about the model that we are developing with the Pavia group about TMD gluon distribution function, which is based on the spectator model approximation. But before to start, I would like to briefly recall some introductory remark about gluon TMDs, the gluon TMD sector, and then general feature of gluon TMDs. We know that while several results have been obtained concerning quark TMDs and the deep knowledge of their formal properties is surrounded by a rich and wealthy phenomenology, from the in the gluon sector, the situation is much more complicated. On one side, from the formal point of view, we know that different gauge link structure appear. This making the situation worse because there is a more diversified kind of modified universality with respect to the quark case. And then from a phenomenological point of view, we know that the golden channels for the extraction of quark TMDs turn out to be subleading for gluon TMDs. So we need to, in some sense, to look for more exclusive final states. So we know that the gluon TMD PDF represent a core research sector of EIC studies, which is our reference colliding machine, but also it is important to perform studies about the gluon on the gluon sector also at the NICA SPD machine and also at the future high luminosity CERN, high luminosity LAC. So we need a flexible model which is suited for phenomenology, and in this sense we build up a model based on the spectator approach, spectator approximation, in which we we calculated unpolarized and polarized gluon TMDs. And we trace the path for also to create a consistent framework also for quark TMDs. Let me remind in this table what are the T-even and the T-odd gluon TMDs at twist true, which are 8. And if we combine them, if we organize them in this table, we have the gluon polarization, unpolarized, circularly polarized, and linearly polarized, and also the nucleon polarization, unpolarized, linearly polarized, and transversely polarized. And we have these 4 T-even gluon TMDs, the unpolarized TMD, the helicity, the T-even Wormgear, and the Bohr-Mulders. Then we have also other 4 TMDs, which are the well-known T-odd 1, the Sivers gluon TMD, the linearity TMD, the Pretzelosity TMD, and the T-odd Wormgear TMD. In this talk, I will present features about the T-even gluon TMDs calculated by us, and also I will point out some prospective developments for the T-odd sector. This is before to go into the details of our model. I would like to briefly remark some properties of gluon TMDs. And we know that in general for all TMDs, and let us start for the quark case, we know that the process dependence of TMD appears via gauge links, and we had the first confirmation of this via the study of single spin asymmetries from the phenomenological point of view. And we know that we can calculate this, we can define what is this process dependence by following the color flow via the integration paths of gauge links, which are calculable. And we know that the gluon TMDs exhibit a more complicated structure with respect to the standard quark staple links. And we know that the process for which the factorization is preserved, or at least for which the factorization we know that it is not proven to be broken, we have two main kinds of modified universality, so 2 main kinds of gluon TMDs, and different class of processes probe these distinct gluon TMDs, which are not related to each other. So borrowing the language of the small x studies, we can define WW Weizsäcker-Williams gluon TMD, which are nothing but a combination of 2 staple links. This, for example, ++ or --- and then we have the dipole gluon TMDs, which are a combination of +- or -- staple links. So this structure leads to a more complex process dependence in the gluon sector. And we know that, for example, we can probe Weizsäcker-Williams gluon TMDs, for example, the ++ or and the --- in this kind of processes. For example, the 2 jet SIDIS allow us to probe the ++ gluon TMD, and we know this because we can take the gauge link, expand it, and consider just the first order of the gluon iconal approximation. And here we see that the color flow points to the future, so we have ++ in this case. But in the case of Higgs, in gluon fusion, for example, or gamma star plus a bound state, like for example, quarkonia heteroproduction, we probe the minus-minus gauge link. On the other side, we can probe the dipole gluon TMDs via the photon jet heteroproduction. And here we see that if we follow the gauge link, we are forced to add a future pointing iconal gluon plus past pointing iconalized gluon, and the same thing for the case of anti-quark generated jet. So we see that in the WW channel, the color flow is annihilated within the final or initial states. And we call these TMDs also F-type gluon TMDs, because when we do the calculation of the parton correlator, the gluon correlator, we see that the antisymmetric color structure appear. And we have a modified universality, which is in some sense the same. It is the same kind of the one we see for quark. So the T-even WW gluon TMDs doesn't change sign, while the T-odd, in this case the representative one is the Sivers, change sign when we pass from plus plus to minus minus. The same thing appears for the dipole gluon TMDs, even if in this case, as we mentioned, color flow involves both initial and final states. And here, when we calculate the gluon correlator, we know that we see that the symmetric color structure appears. So we call these TMDs also D-type gluon TMDs. And we see that this dependence on gauge link makes us to have two main independent set of TMDs which are not related to each other. Then, in principle, I mentioned here the general, the two main kind of gluon TMDs, but there are more complicated gauge link structure. And for example, they appear in the dihedron heteroproduction, but we know that this process makes a factorization to be violated. And for example, we can do studies assuming factorization in scaton color glass condenses and color glass condensate. And this, in general, this kind of final states is important in low X studies. And we, in principle, we need to continue the study on this process to investigate and to gauge the size of factorization breaking effects. And in this case, we don't have just the dipole TMDs, but we see the appearance of new gauge loop links, which are this one, but we will not discuss about them in this talk. So let us go to the main results and to the core, then the general feature of our model. So let's discuss the assumption. The assumption of the standard, the basic assumption of the spectator model is that the nucleon here, Me, which has a mass m and a momentum p, capital P, emits a gluon and the remainder is treated as an effective spin 1/2 spectator particle. In principle, we can describe this spectator particle also as a spin 3/2 particle, but just for our starting point, for simplicity, we consider it just as a spin 1/2 spectator. And here we need to model the effective vertex. And here we model this vertex, this Y, as a combination of two structures, gamma mu and sigma mu nu p nu, which are multiplied, but a priori general function, which depends on the momentum of the structured gluon. And in principle, this vertex could contain more structure, but we consider just the two ones to recover the conserved electromagnetic current of a free nucleon. The other assumption of the model is the link of collinear factorization. And let me stress that in this case, we are not considering a gluon correlator of QCD, calculated in QCD, but it's just a model which allows us to describe the non-perturbative, the non-evolved part of our distribution. So we can safely assume this link with collinear factorization, that the PT integrated TMD have to reproduce parton distribution function at the lowest scale, which is Q0 and depends on the parametrization of the collinear PDF used before evolution. So once we have this model, which is given in terms of this spectator model, then we can switch convolution on and recover a full and completely consistent gluon TMD. And then as for the dipolar factor, here we use this, for the form factor, we use this dipolar expression for both for both G1 and G2 function. This allows us to cancel singularity of gluon propagator, suppress effect of high PT, so our calculation is safe, and compensate log divergence arising from PT integration. This makes us add three more parameters that will be fixed by our fitting procedure. This K1 and K2 constant, and then the normalization constant, and then this lambda x cutoff. Okay, we improved the standard spectator description by considering not just a single on-shell spectator emitted by the proton when the gluon is struck, by integrating weighting this spectator by a suitable spectral mass. So instead of a single on-shell spectator, we have a continuum of spectators. So taking into account of our assumption, in particular, the inclusion of a spectral mass function and the link with collinear factorization, we performed a fit in which our spectral function, which is given in terms of a number of parameters, learns both the small and the moderate XX information encoded in the parametrization of collinear PDF. Here, for example, we used the neural network collinear parametrization because the NN-PDF collaboration improved the description of the unpolarized PDF by considering effects, small x effects coming from the BFK resummation. So here, from the effective point of view, we included small x effect in our parametrization. And then we performed a simultaneous fit also, not only on the unpolarized, but also on the longitudinal polarized, on the helicity PDF. We included, as I mentioned, a small x effect, and this allowed us, by these fitting procedures, our parameters, the calculation of all T2T even gluon TMDs. The result, this is just one slide about fit specifics. The result of chi-square is one, so we have a rather small chi-square, but this is not due to overlearning, to overfitting issues, but just large error for G1 collinear PDF, as we can see here. And this is the result of for example, of the second Mellin moment of our PDF, which is the nucleon, which corresponds to the nuclear momentum fraction carried by the gluon at the model scale, which is Q0, and I forgot to mention is set to 1.64 GeV because it is the lowest scale provided by neural network PDF. And then here we have the first Mellin moment of the G1, which gives us the contribution of the gluon helicity to the nucleon spin. Here we can compare the result for our model and then for the lattice one recently calculated at 2 GeV, so on a similar scale, and we see that we are in excellent agreement, even if in this case we are comparing different quantity, for example, for the angular momentum. Here we have the spin, but they have the total orbital angular momentum. The total angular momentum. And here I want to show a plot about the unpolarized gluon TMD, for example, at x equals 0.1, and we see the behavior of this gluon TMD versus PT squared. And there are, of course, I stress here that we still have to include evolution effects. So we are seeing the non-perturbative content, non-evolved content of our parametrization. And here we see here that we appreciate a non-Gaussian shape in PT with a large flattening tail for PT that tends to 1 GeV. And also here it is difficult to see from this plot, but we have a very small button of vanishing value for PT that tends to 0. Then you have 2 minutes. Thanks, many thanks. Then when we increase the X, of course, the bulk of our distribution stay at small PT, and this is encouraging because this is consistent with the TMD framework. But of course, the peak increases because we are probing how TMDs and also by reference the collinear PDF at smaller X. And here I briefly want to show some preliminary image, about 3D tomography. I call it preliminary, of course, because we didn't switch on evolution yet. And here we see the unpolarized TMD in this contour plot, in which we see the size of oscillation in the PT plane, so Px and Py, and the color code gives us this size of oscillation. Since this TMD is completely unpolarized, we see a completely symmetrical and cylindrical symmetry, which is partially broken in the Bohr-Mulder's case because we have an effect of polarization of the gluon, and here we see this quadrupolar structure. And then the Warm-Gear TMD is asymmetric, is slightly asymmetric, and this asymmetry is due to the fact that here we see we are probing a completely polarized TMD from the nuclear point of view, and also from the from the part for the gluon point of view. Then I would like to mention how efforts to reach to have a calculation of also of these two T-odd gluon TMDs, which are this one. I remind you again: Sivers, linearity, Pretzelosity, and T-odd worm gear. And we see that if we will do just this three-level calculation, we will have no residual gluon-spectator interaction. So we need to encode the interference with one gluon exchange. So this diagram here, because let me remind that in the even case we don't have this one gluon exchange in the diagonal approximation, so we have just three-level calculation. And here we have, for example, F-type in GG2 Higgs and D-type in photon jet hadron production. So this is nothing but the leading twist one gluon exchange of the gauge link operator. And when we do this calculation, we are not only able to calculate the T-odd TMDs, but also we gain the sensitivity to WW and dipole gluon TMD structure. And the calculation of the first of the four ones, in particular the Sivers function, is underway. So just to conclude, we performed a systematic calculation of all twist-2 even gluon TMDs. We added the spectral mass to catch small and large X effect, and we performed a simultaneous fit of F1 and G1 PDF via the replicate method. We are working on calculating the T-odd gluon TMDs that will be soon available. From the phenomenological point of view, we would like to investigate spin asymmetry and also generate pseudodata and perform impact studies. And then, as we would like to include evolution, understand this calculation of two quark TMDs in the same framework, and perform explorative studies on gauge link sensitivity, of course, a factorization, as well as in the medium-term future, perform study on GPD and small x UGD sector. My time is over. I left you just with this slide about a possible application from the phenomenological point of view to quarkonia. And quarkonia are important because we are able to probe not only the WW gluon TMD, but also considering the production mechanism of the quarkonium state. And here I will not discuss, but I mentioned just some recent progresses on the phenomenology at TAC, NICA, and high luminosity LAC. Thanks for the attention.
Thank you very much. Now open for discussion. If you have any question, comment, please raise your hand. Carlo?
Hi, Francesco.
Hi.
Quick curiosity.
Yes.
As I understood, when you consider unpolarized TMDs, for example, for gluon, then you do a sort of matching to the collinear unpolarized PDFs, right?
Yes, in the sense that we fit the parameters to the integrated TMDs. Yes.
Okay, I was wondering what's your idea for the Sivers function that has not any collinear counterpart at the twist?
Oh yes, yes. Okay. As for the model, the first thing we can do is assume parameter fixed by the fit we have already done. So when you calculate this Sivers function in the spectator model, and then you weigh this by the via this spectral mass, you already have the parameters fixed. Of course, when you do this, you are doing some choice, some approximation. For example, you are assuming that this vertex, which appears when you have the interference with one gluon exchange in the diagonal approximation, is the same of the one that in which we have the emission of the gluon, because otherwise you have further parameter and you have to decide how to fix them. So for the time being, we would like to stay with the parameter fixed by the fit on unpolarized and helicity, and then in the future gauge the sensitivity to including when we include including also new parameters.
Okay. Okay. Thank you very much.
You're welcome.
All right. Anyone else have question? If not, thank you again for the speaker. This was the last talk of the session today. Thank you everyone for joining, and especially all the speakers for delivering excellent talks and discussion. So after this talk, we have the interactive discussion session for the flash talk starting from 2:15 Eastern time, but gather time should be available all the time. So please join the gather time and look around the poster and flash talk presenters and have discussion or with other colleagues. Tomorrow, the parallel session will start at 8 a.m. In New York time. So I hope to see you all again tomorrow sessions. Thank you, everyone. Have a great afternoon and night for the colleague from Europe and Asia. Thank you.
Thank you. Goodbye.
Thank you.